I'd like to introduce Kyle Leik, presenting effects of electromagnetic energy on electronics. Kyle works in the high power electromagnetics group of Applied Research Associates. He runs the Electromagnetics Testing and Technology Development Center in San Antonio, Texas. This is Kyle's first time presenting at NANOG, and we're certainly happy to have him speaking with us today. Welcome, Kyle.
Good morning. Yeah, this is certainly my first NANOG because I've been calling it NANOG this whole time. Just learned that that's not how you say that. So I realize that this talk seems a little bit out of scope from a lot of the other talks that are typically given here, but the motivation really is to talk about a threat to data centers and network infrastructure in general that's often overlooked. I know that there's a lot of time and effort spent into ensuring the reliability of data centers and the infrastructure around them, accounting for physical security and redundant power source and backup data storage. But what's often not considered is electromagnetic threats. So during this presentation, I'm going to give a variety of sources of electromagnetic threats and how you can mitigate them. So the outline of this talk, there are 3 EM threats I'm going to talk about. The first being geomagnetic disturbances. We're going to move on to the high altitude nuclear detonations that give rise to electromagnetic pulses. The last one's going to be intentional electromagnetic interference, or just EMI, some people call it. And then finally talk about how you can protect yourselves and then mitigate these effects. So before I actually jump into this, I want to talk about the mechanism by which electromagnetic energy is actually going to damage electronics. So much like an antenna works, it's a conductor that's meant to pick up electronic energy, right? But when electric fields are so large, they can actually drive currents on places that currents are not supposed to be going. And if you get a large enough current in a small enough area, you can get heat in, you can burn out devices. Sometimes just driving current where it's not supposed to go can flip transistors and turns parts of your circuitry on that should not be on anymore. And it's these kind of variations that lead to damage in your equipment. So, let's see, shouldn't be there. First talk, or the first subject is about geomagnetic disturbances. And generally what happens in these types of events, you have high energy particles from the sun, typically protons, electrons, alpha particles that interact with air of the atmosphere, and it creates this hot ionized pocket of air, really. And this pocket interacts with our geomagnetic field to create electromagnetic radiation. And now, typically this happens in concentrations that are so small that the effects are typically benign, and you only see effects if you're doing something like launching 49 satellites into orbit, and you suddenly lose 40 of them. In that case, it wasn't really an electromagnetic effect. It had to do with a denser pocket of air intercepting the path of these satellites, and just the increased drag on them slowed them down to cause them to fall into orbit or fall out of orbit. So this steady stream of particles from the sun, typically called solar wind, is, it's always hitting the Earth, and typically our geomagnetic field protects us from it. It concentrates its particles toward the pole. But if you get enough of them, such as in a coronal mass ejection, it can become a large issue. The interactions between the ions of the atmosphere and our geomagnetic field produce strong EM radiation, and these are typically low frequency signals, and low frequencies like to couple to long conductors such as transmission lines and communication lines, maybe long Ethernet cords, that kind of thing. And so because the power grid, of course, is made up of a lot of very long conductors, it's particularly vulnerable to a geomagnetic storm. And things like this have happened before. So back in 1989, we had what's called the Hydro-Quebec event, or sometimes called the Great Geomagnetic Storm. But for about 2 to 3 days, there was a burst of impulses from the sun that were focused along the US-Canada border. And so this resulted in large currents being driven on these transmission lines, and actually tripped a lot of circuit breakers that were handled in the grid in the Quebec area, and the entire city was without power for hours that day. And then, down in the States here, there's a nuclear plant in Salem, New Jersey, and that experienced a particularly devastating effect. One of the transformers, which is actually shown over here, so much current was driven into it that the insulation on wires evaporated, wires melted together. And these large transformers are not something that you can just buy a new one and replace. It can take months to get one. So in this case, only one transformer went out. But if you have many of these things going out, you could have portions of your grid down for months to over a year. Now, even before that event, before we actually had power lines crisscrossing the nation, we still had telegraph lines all around. The Carrington event, 1859, about a little more than 100 years before the Quebec event. It's typically regarded as the largest recorded geomagnetic disturbance. And so at that time, telegraph operators were reporting that they were being shocked by their equipment. Some said that they could send signals down their line without even having to supply power to them. General corruption in the signals that were being sent. And the same thing could happen today on communication lines. Whenever you're putting power on these lines, it's not supposed to be there. It can interact with your intended signal. If a similar event in magnitude to the Carrington event were to happen today, a Lloyd's of London report estimated between $600 billion to $2.6 trillion in damage, and you get that kind of damage from these large transformers going out in data centers, in substations, and then taking out equipment in data centers, taking things offline for large periods of time. Even if you do have backup generators, how long can they run for? If the grid is down for pushing a year, you're not going to have enough fuel to keep it going all the time. And this is it's a serious enough threat that there have been multiple documents issued by the government directing for the protection of critical infrastructure, so power grid, financial systems and banking systems, communication networks. So the next source of electromagnetic energy I'm going to talk about is the EMP, an electromagnetic pulse from a high altitude nuclear detonation. So what's shown in this contour plot here is peak electric field. In the background, you can make out the continental United States. And so you can see the range of impact that an event like this could happen. When a nuclear weapon is detonated, among other things, it releases gamma rays in the atmosphere. And these gamma rays serve to strip electrons away from air molecules. And you end up with this high energy current in the atmosphere that again is turned by the geomagnetic field, and this creates a propagating electromagnetic pulse. Now, this is something that on the ground can lead to tens of thousands of volts per meter, huge electric fields, and it gets up to those levels in billionths of a second. It's very fast. Now, like geomagnetic disturbances, there are some very low frequency signals in EMP that will couple to your power grid and your transmission lines in general. There are also a lot of very high frequencies, and it's the high frequency signals that can be damaging to smaller electronics, your computers, your routers, your switches. And that's not just theoretical. We do testing to show that kind of thing does happen. One of the first times that people started to actually piece together that EMP was a thing resulting from nuclear weapons, at the time they didn't call it EMP, they called it radio flash. But while we were doing above ground testing, this one took place in 1962, people were noticing effects on their electronic equipment resulting from them. Starfish Prime was a 1.4 megaton nuclear weapon. If you're not familiar with megaton, it's equivalent of 1.4 million tons of TNT equivalent. And about 1,000 miles away in Hawaii, people were noticing effects. In addition to satellites in orbit that were taken out, folks noticing that burglar alarms are being set off, parts of their power grid were being disabled, telephone and radio services were going down. And while America was doing this kind of testing, other countries were doing similar testing as well. The K3-184 nuclear test was done by Russians, same year as the Starfish Prime test, and similar effects were seen. There were reports of power supplies for radio equipment, burn it up so the radio equipment became useless, and just anything in the area connected to a long conductor is pretty much blown out. In March of 2019, an executive order was issued that directs the strengthening of our critical infrastructure to EMP specifically. Like the one issued for geomagnetic storms, it calls for the protection of our power grid and banking and financial systems and federal networks in general. There are already power utilities and financial institutes that are investing in protecting their infrastructure from general electromagnetic threats in general. Joint Base San Antonio down the road has organized an electromagnetic defense initiative. And the goal of this is to ensure the resiliency of not only their power grid, but also a lot of the new 5G equipment that's being installed around the city. And it's very important that this kind of equipment is protected because we know it is vulnerable. We do EMP testing. Now, of course, we're not actually setting off a nuclear weapon and seeing what happens to it. The DoD maintains these large-scale EMP simulators where testing can occur. And in these situations, the picture here is showing a test of a lot of IT equipment. We set this all up in a functional way. It's working before we test it. And it's important that that happen. One, because it's important that all of the conductive connections that are made to these devices are actually there because they all serve as antennas to drive energy into the device. And also we want to make sure it's working because then when you zap it, you know, if something goes wrong, you could say that you actually broke it because it used to be working. So Hollywood gives people this idea that if an EMP event were to happen, that planes would fall from the sky and your phones would explode, that kind of thing. And it's just simply not true. There are a lot of things that would generally be okay. Small devices like your cell phone would generally be fine. Who knows if there'd be an actual cell network to make them useful? That's a different story. But as long as your phone isn't, say, connected to a power cord that can drive energy into it, it'd probably be fine. There are instances where things are just temporarily upset. We've seen computers that will just freeze. And your IT department will be happy to know that you can just turn it off and on again and it'll be fine. And then sometimes things are actually damaged. So things connected to Ethernet cords are particularly vulnerable just because these long Ethernet cords channel a lot of energy into these ports. Sometimes you can blow out the port permanently. Sometimes they'll come back online. Sometimes the switch or the router is okay and you can just move your cord to another port, but it all depends. Okay, the final source of electromagnetic energy I'm going to talk about is intentional electromagnetic interference. And some people consider this the most worrisome in terms of likelihood and severity of effect. You know, geomagnetic storms are something that are certainly going to happen one day, but the actual effect of them is going to be unknown. It's going to be related to how strong the storm is. A nuclear EMP is something that we hope never happens. IEMI is something that very realistically could be done. And unlike the last two sources of EM I talked about, this is something that's a more localized attack, and it's something that can be carried out by individuals rather than Mother Nature or state-sponsored activities. IEMI comes in a variety of forms, and really any type of electromagnetic radiation that is intended to interfere with or damage electronic equipment can be considered IEMI. Some of the devices are built to target specific equipment. Say somebody knows about a particular make and model of a piece of vital equipment you use, they can make an IE device to target that particular piece of equipment. But a lot of times people build these devices just to jam the airwaves and kind of take out anything that is trying to receive a signal. Shown in this photo, this is a suitcase-sized, high-powered microwave source, and this is something an individual could, say, try to sneak into a facility. Say they know that the bathroom shares a wall with a server room. You know, maybe they're able to get into the bathroom and they plant the suitcase device in there, pointed at your equipment. And things like this do happen. What I have here is a list of some cases I was able to dig up about IEMI instances over the world. 3 of them are pretty much the intention is criminal activity, robbery in general. The first item here is a man using an EM disruptor to trigger a win in a gaming machine. That's considered thievery. But then there are also folks that are able to disarm security systems. So there was a case of a man in, I think it was Russia, who was able to build one of these devices, disarm a jewelry store security system, and just get in and get out. And folks have also done this with security systems on limousines that were meant to use a cellular network to call out to get help. Disabled, they couldn't call out. There are also cases of Chechen rebels using similar devices to take out police radio systems and then gain access to controlled areas. The last one here is an instance of revenge. A man in the Netherlands was denied a bank loan, and he wasn't too happy about that. He went online, learned how to make an EM disruptor, and was able to take out their IT system for a few hours before they tracked him down. And what's scary is that all the things I just talked about, they're not things you have to be particularly tech savvy to do. You can look online at how to build these things. You don't have to be very knowledgeable. And if you don't even want to do that, you can just buy them. This suitcase HPM source right here, a company in Austin makes it. You can buy it from them. This is designed for testing, scientific purposes, of course. I doubt they would sell it to you if you were just your average Joe. At least I hope not. The other two devices here I found on eBay, not too expensive either. They're meant to jam cellular networks and GPS signals. Probably on a list somewhere from looking all this stuff up, though. Okay, so, it's not all doom and gloom. There are ways that you can protect yourself from electromagnetic threats, and that's when we get into shielding and hardening. So in this little figure here, the idea this is trying to convey is that you don't always have to block all of the electromagnetic radiation. You just have to get it down to levels that are safe. It's not enough power to actually damage equipment. So I'm sure a lot of you are familiar with the concept of a Faraday cage. It's a conductive enclosure that electromagnetic radiation cannot enter. An ideal shield would be, say, a hollow conductive sphere, but of course there are issues with this sphere, like you can't get anything in or out of it. You need a door, and for shielded enclosures like this, there are specially designed doors such that when it's closed, it forms a fully conductive seam around the door. Usually they're installed in pairs in a man-trap configuration, so only one can be opened at a time. Although that's not always foolproof. I've seen situations where people will override the system and prop open both doors because they're complaining they couldn't get a cell signal inside. It's like, that's the point. What's important to consider with something like a Faraday cage and shielding in general is it's not a situation where every little bit of shielding helps. It's really an all or nothing situation. As soon as there's a small crack in the shield, it's a place where electromagnetic energy can get in and damage your equipment. Your shield might as well not even be there. And now I realize that what I just said might conflict with the photo I'm showing here of this RF shielded rack that has a whole array of holes in it. These are actually what's called waveguides below cutoff. These are devices that maintain a certain ratio of width to distance such that EM energy that goes into them is exponentially attenuated. So by the time it gets in, it's so low level, it's not going to harm your equipment at all. And these WBCs, they're good for passing non-conductive things into your shield. So fiber optic cables, or in this case, it's shown as for ventilation. So air moves in and out. What they're not for is to pass your TV antenna through so you can watch TV, because that's just a channel for EM energy to come in. I've seen that happen as well. I've also seen the case where somebody tried to, there was a bank putting together a server room and they wanted to shield it. And they were talking to my team to see if the shield was going to be effective. I asked what the shielded material was made out of. They said they'd get back to me, and the next week they sent me in the mail a sample of the material that they had cut right out of their shield. And so it doesn't matter what it's made out of. There's a huge hole in your shield. I can promise you it's not working. But of course you can't, or you don't only need to bring non-conductive things into a shielded enclosure. You need to bring things like power and maybe signals. And so to bring those kinds of things into a shelter, you can use filters that are good for, say, directed anything above the 60 hertz electric signal you want to see to ground, and then various forms of transient voltage suppression, MOVs, GTDs, and these things will short over voltages to ground and just bypass your shielded enclosure. And then even if you don't want to implement these kind of hardcore shielding approaches, there are ways that you can mitigate what effect an EM threat would actually have on your facility. So I'm sure data centers, you guys are all familiar with having backup generators, up systems, automatic transfer switches. How often are drills conducted? You know, do you know, first of all, this equipment is functional? Do people know what's going to happen if, say, your automatic transfer switch doesn't switch? Do they know what to do and who to go to? And is that person contactable when this kind of thing happens? It's also important to keep distance, just physical distance between your important equipment and any publicly accessible location. That really mitigates a lot of the IEMI effects. It's also very helpful to use non-conductive material where possible. Fiber optic cables are strongly recommended. Or if you have to use Ethernet cords, keep them as short as possible. And some things you can do right now, some simple ways to improve it. Again, shorten the Ethernet cables. They sell these ferrites. You may see them on the end of power cables, they're little beads. And what they do is they increase the inductance of conductors, and it prevents high frequency signals from being driven on them. That's what's shown in the upper right here. And then below that, the point I just want to make with that photo is one, keep everything organized so that cables are no longer than they need to be. And then two, if you find yourself in a situation where you need to, say, swap out an Ethernet cable because the port was blown, it's going to be very difficult to find where that cable actually went if it's not organized. Well, went a little fast, but that's it for me. Are there any questions?
So do we have any questions in the room? Anybody? Okay, I do not see any questions in the Q&A chat. If you are in the chat and you have questions, please post them in the next minute or two. Okay, I don't think we have any questions, so thank you very much.
Yeah, thank you.